This video is for lesson 8-4 about parabolas. Parabolas is something that we saw in an earlier chapter when we graphed quadratic equations. We just learned in the last section that the set of points that are equidistant from a given point is a circle. There are other geometric figures that can also be defined as sets of points that satisfy certain conditions. In this figure, notice you see a parabola. This shows the set of points whose distance from point 3, 4 is equal to the distance to the line y equals -2. Here is point 3, 4. It's given the letter F. And here on the grid is this horizontal line crossing the y-axis at -2. This is the line y equals -2. If you measure from that dot to a point on the parabola, but then measure from that point, point P, straight down to the line, you get equal distances. This is equal to this distance. Or if you measured from this point to right there, and then measured straight down to the line, these distances would be equal. Or if you measured from that point, point F, straight down to the vertex point, and then went from the vertex point down to the line y equals -2, these distances are equal. So it's possible to describe a parabola in terms of equal distances. A parabola is the shape created when you make the distance from this dot here, called point F, to any point on the parabola, make that distance equal to the distance from that point straight down to some horizontal line. On the internet, there's a GeoGebra animation that allows us to explore parabolas a little bit. Let me click that link. Here's the dynamic animation of a parabola. This is better than that drawing we were just looking at because we can manipulate things. Here's point F. This dot right here is the vertex of the blue parabola, and the orange line is a horizontal line. We're later going to learn that's called the directrix line. Based upon what we were just discussing, the distance between point F to any point on the parabola, in this case point A, is equal to the distance from point A straight down to touching the directrix line. As I move point A, notice the green dashed lines move, but the distances remain equal. When point A is right at the vertex, the distance from A to F is 1.4. The distance from A to the directrix line is also 1.4. This animation gives that the variable P, and we can control the value of P with this slider. So as the distance increases between point A and point F, look what's happening to the parabola. It's widening. If I drag it back towards this direction, it gets narrower. What do you think will happen when P becomes negative? The parabola flips upside down and goes downhill. We saw those kinds of parabolas in an earlier chapter. In this animation, we can also control the values of H and K, which we know from that earlier chapter is the vertex of the parabola. So instead of being at 0, 0, maybe we want the vertex to be at 1, 2. And this animation moves the parabola to correspond. The point is that a parabola is a shape that's created by keeping some distances equal to each other. It's the distance between a dot called F. We're later going to learn that's called the focus of the parabola. From that dot to a point on the parabola, that distance is equal to that point on the parabola to a line, which is called the directrix line. Let's go back to our notes. In our drawing, we had discussed that in a parabola, the distance from F to point P on the parabola is equal to the distance from point P to a point on the directrix line. Because those are equal to each other, we can apply the distance formula. You see the work shown on the screen. When appropriate coordinates are plugged into the different places, and it is simplified, we end up getting this equation. Hopefully you recognize the format of this equation from the earlier chapter. This is vertex form. Here's our value of A, here's our value of H, and here's our value of K. The H and K get us the vertex. The value of A helps us to know if it goes up or down, and also tells us how wide the parabola is. In our parabola, the axis of symmetry goes through the vertex, but it also goes through point F. The vocabulary word for point F is called the focus point. The vertex point is midway between the focus and a line. And as already mentioned, the vocab word for the line is directrix. The axis of symmetry is perpendicular to the directrix. In Chapter 6, we saw parabolas that were functions. They open up or they open down. But there are also parabolas that aren't functions. They open to the left or to the right. For example, a parabola might look like this. This is not a function because it violates the vertical line test. If you draw a vertical line through it, this dot is lined up vertically with this dot. That's when it's not a function. A parabola might also open to the right, like this. This is not a function either. But for both of these, it's possible to create an equation that fits that geometric shape. Here's an example problem. Let's find an equation for a parabola. And here's what we're given about it. We know the focus point. It's -2, 0. And we know the directrix line. It's x equals 2. Let's draw the parabola and label a whole bunch of stuff about it and find the equation. What we can draw so far is that at -2, 0 is the focus point. Let's call that F for focus. And x equals +2 is the directrix line. So we can draw a vertical line crossing the x-axis at +2. This is the equation, x equals 2. Because the focus is located here and the directrix is over here, can you predict how the parabola is oriented? Well, one thing we learned today is the vertex point is midway between the focus and the directrix. So as you travel from the focus straight towards the directrix, when you get halfway, there's the vertex of the parabola. Let's call that point V. I think the parabola is going to open up like this. Now this is not an accurate picture of the parabola. To get an accurate picture, we actually need dots. And to find dots, we're going to need the equation, which is what this question asks us. To find the equation, let's use the definition of a parabola discussed today. The distance from point F to a point on the parabola, let's call it point P, this distance right here, is equal to the distance from point P over to the directrix line. Let's call this point D. Let's think about the coordinates of these points. Point F we know for sure is at -2, 0. That was given to us. But point P is any random point on the parabola. Let's call its coordinates x, y. For point D, which is on the directrix, we know for sure that its x-coordinate is 2. And we can see that it's at the same height on the paper as point P, which has a y-coordinate of y. Now that we've labeled our ordered pairs, let's make our equation. We know that the distance from F to P is equal to the distance from P to D. Let's model those distances with the distance formula. That involves doing square roots. Here's our basic setup. On the left side, let's fill numbers in from F and from P. We subtract the x-coordinates, so we have x take away -2. And in here we subtract our y-coordinates, y take away 0. Now on the right side, let's look at point P and point D. Subtract the x's and subtract the y's. This is x minus 2, and then y minus y. Now let's simplify on this side. In the square root, x plus 2 squared, and then plus y squared. On the right side, let's simplify. We have x minus 2 squared, and then this part here just turns out to be 0. Now remove the square root by squaring both sides. So now we have x plus 2 squared plus y squared is equal to x minus 2 squared. This first part right here is squaring a binomial. Let's expand that. X squared plus 4x plus 4. Then there's the plus y squared. On the right side, this is another instance of squaring a binomial. Let's expand that. X squared minus 4x plus 4. There's an x squared on both sides, so using subtraction, those will cancel away. There's a positive 4 on both sides, so when you subtract 4, those will cancel away. Next step, add 4x to both sides to remove this negative 4x. We get 8x plus y squared equals 0. Next up, subtract y squared from both sides. We have 8x equals negative y squared. And finally, to get x alone, divide by 8. So we have x equals negative 1 over 8 y squared. Here's the equation for our parabola. Unlike the earlier chapter where parabolas opened up and down, our parabola opens to the left. And notice it has the letter x alone. It goes x equals. And the thing that's squared is the letter y. In the earlier chapter, the equation went y equals. And the thing that was squared was the letter x. Because this is a negative here, the parabola is opening to the left. This turns out to be positive when parabolas open to the right. Now that we have an equation, we could make an accurate graph. You would plug numbers in for y and see what x makes. For example, when y is 2, what do you get for x? You would go 2 squared makes 4, and the negative 1/8 times 4 makes negative 1/2. So now we know for sure that left a half, up positive 2 is a dot on the graph. See when I made my little blue dashed line? I actually was very close to that red dot. There will be a corresponding dot right here. We could choose another number for y, such as 3. 3 squared makes 9, and negative 1/8 times 9 is negative 1 1/8. So negative 1 and an extra little bit to the left, and then up to 3. Whoops, my dashed blue line that I sketched earlier is a little bit farther away from where it was supposed to be that time. And there's a corresponding dot right here. Let's find just one more. What about when y is 6? 6 squared is 36. And negative 1/8 times 36 makes negative 4.5. So here's negative 4.5, and the dot's up at 6. And a corresponding dot down here. You can see my blue dashed line now is not very close to where it's supposed to be. Now that we have accurate dots, we could draw in the parabola. Here it is in red ink. Much better than that blue one that I had done earlier, just guessing. Next one, sketch the shape of the parabola. So we don't need to make an accurate graph, and we don't even have to find the focus and the vertex and all those things. We just need to predict the shape. Okay, this one has the letter y alone, and it's x that's squared. That was our earlier chapter. And the value of a is positive. That's when the parabola opened up. What do you think this one's going to be? This time it's the letter x that's alone, and it's the y that's squared. So it's the kind of parabola that's on its side. And because this is negative, the parabola opens to the left. What do you think this next one here is? This one has the letter x alone. It's the y that's squared, so it opens sideways, but this time a is positive. So the parabola opens to the right. One more to go, but I notice I have a typo in here. Will you make that be the letter x if I didn't already fix that on your notes? Okay, now predict that one. This time the parabola opens down. The reason is it's the letter y that's alone, and it has a negative value of a. Let's summarize the lesson. We reviewed parabolas, which we had done in an earlier chapter, but we defined the parabola as a geometric shape. A parabola is the shape created by keeping two distances equal to each other. The distance from a point called the focus to a point on the parabola, and the distance from that point to a point on a line called the directrix. In our example problem, we actually made the equation of a parabola when given some information about it, and we used our equation to accurately find dots to graph.